Welcome to the presentation of our work on Baital, an adaptive weighted sampling approach for improved device coverage. In modern world, many systems are configurable, where a user can select among many options and build a version of a system that is suitable for his needs. Options are often called features, and the selection of features is a configuration. In most of the cases, not all configurations are valid. There could be some dependencies on features that make some configurations invalid. For example, one feature cannot be selected without another one, or two features cannot be selected together. As a result, configurable systems usually contain a set of constraints on features that describe how to build valid configurations. A question arises: how to test configurable systems? Clearly, it is not enough to test a single configuration. All features that are not involved in it are not tested at all. On the other hand, it is not feasible to test all configurations. Their number grows exponentially with the number of features. In the 1980s, a combinatorial interaction testing approach had been proposed, where we built a set of configurations that covers all feature combinations of size t. For example, if we consider pairs of features, we need to have all pairs of features, so feature 1 and feature 2, feature 1 and feature 3, feature 2 and feature 3, in one of the configurations in this test set. And also we need to include non-selection of features as well in the combinations. For example, so we not only speaking about feature 1 and feature 2, but also about non-selection of feature 1 and feature 2, feature 1 and non-selection of feature 2, and non-selection of both features. The test set built in this approach is usually much smaller than the set of all configurations, and this is often used for testing the configurable systems. However, in case of large systems, there could be problems. First of all, it might be too complex to compute the test set that covers all feature combinations, and also, in case of complex constraints, the test set can be too large for testing. For example, we have a testing budget to test 100 configurations, however the computed test set has thousands of them. An alternative approach is uniform sampling that uniformly selects configurations among all valid ones. Uniformly means that all configurations have equal probabilities to be selected. With this approach, we can build a fixed size test set, so we require to sample exactly the required number of configurations, for example 100. However, with this approach we lose a guarantee to cover all possible feature combinations. Though many works argue that this approach is still good at finding faults. To measure the quality of the test sets generated with uniform sampling, we use a metric which is called device coverage, which is a ratio between the number of covered feature combinations by the test set and the number of all valid combinations of size t. In our work, we would like to build a test set that has a better device coverage than one could be generated with uniform sampling. To show the limitations of uniform sampling, we propose the following example. So this is a configurable system of a graph library, very simple one. It must support the edges, since all graphs except very basic ones have edges between nodes, and the edges can be of two types, directed and indirected. And the library could also support some algorithms, for example, pathfinding algorithms and cycle detection. However, we have an additional constraint that the cycle detection algorithm requires directed edges. On the left of the slide, we show 6 valid configurations of this configurable system, where we denote each feature with this first letter. So D stands for directed, A stands for algorithms, and so on. Also, we exclude features, graph library, and edges from our configurations, since they have to appear in all of them. So now we want to build a test set to test several configurations of this configurable system. So let's start with uniform sampling and assume we have selected two configurations, DAP and DAPC. And now we can select one more configuration. So what would be the effect of the first configuration on the resulted coverage? If we select the configuration D, we would add several different feature combinations to our test set. If we select the configuration U, we would add 10 different feature combinations. However, if we would select the configuration DAC, we would add only 4 different feature combinations. The problem of uniform sampling is that it has equal probabilities to select any of these 4 configurations. So the chances to select the configuration U are pretty small. So, question is, can we look at already selected configurations and estimate how new configurations would affect our test set and guide the sampling process based on this information? So our approach based on this idea, we call it an adaptive weighted sampling, where we dynamically modify the probabilities of configurations to be selected. What we do, we explore the previously selected configurations in our test set, and we see which feature combinations are covered and which ones are uncovered. And then we modify the probabilities of other configurations to be selected by assigning different weights, giving more weights to configurations that have more uncovered features and smaller weights to configurations that have fewer uncovered feature combinations. And indeed, these updates of probabilities shall be done periodically. We cannot do it a single time, but we have to do it in rounds. We generate several configurations, we select several configurations, then we explore them and assign new weights to the remaining configurations. We select the next group of configurations and repeat the process. So we have implemented our approach in a tool which is called Baital. It takes an input, a CNF formula representing the constraints of a configuration system. Most of the uniform sampling tools take the same input. In our tool, we are required to have a sampler that can select configurations with a non-uniform distribution. We use an open source tool which is called VAPC, which is a literal weighted sampler. So the probability distribution in the sampler is specified by assigning weights to literals, so to a variable of the CNF formula and a weight to the negation of this variable. And in our tool, as I've said before, the execution is done in several rounds. Each round we call the WAPC tool to select several configurations, and in between the rounds we compute the new sets of weights and update them. So the algorithms is pretty simple, is shown here. We start with an empty test set, and then we repeat the number of rounds times the simple thing. So we compute the weights for the round based on the current version of the test set, and then we call the WAPC tool to select several configurations to our test set. And then we extend our test set with newly selected configurations. So in this algorithm we have the select configurations function, which is basically a call to the WAPC tool, and the generate weights is explained in the next slide. So in the weight generation, we took every feature or every variable of the CNF formula, and we check how many combinations involving this feature is covered in the current version of the test set. And we also look for the number of combinations involving non-selection of the same feature or the same variable, and we compare the results. And then we decrease weight of the feature of the variable if it has better coverage, and increase it if the non-selection has better coverage. Returning to our previous example, so as before, we have selected two configurations, DAP and DAPC, and we can see that, for example, feature A algorithms is used in both selected configurations, and there are already several feature combinations covered involving this feature. On the other hand, non-selection of A is not covered in these configurations at all. Therefore, we shall decrease the weight of algorithms for the next round. The same happens for directed and path features. On the other hand, if we look at U, we see that we haven't selected it before, though non-selection of U present in both configurations. Therefore, we shall increase the weight of U. This way, we actually provide a much higher probability to select a configuration U in the next round as before. Since we increase the weight of U, we increase the weight of non-selection of D, of non-selection of A, and of non-selection of P. We have several versions to generate weights that have different complexity. Our base approach is based on the idea we've described before. So first of all, we need to pre-compute the number of feature combinations for each literal, so for each feature and for its non-selection. And then when I say that we compare the coverage of a feature and of non-selection of feature in the current test set, we actually compare the ratio of covered combinations. So this approach is good, however, the precomputation might be too complex in case of thousands of variables in the CNF formula. So we propose the first heuristic, so the version which we call optimization 1 in this presentation, where we don't do the precomputation of the number of feature combinations for each literal, and instead of comparing the ratio between the number of covered combinations and the total number of combinations, we simply compare the total number of covered combinations in the current test set. And the second idea that we call optimization 2, what would happen if we don't actually compute the number of feature combinations that are already covered, but we just look at the literal and see how often it has been selected in the current test set. Would it suffice to guide the selection process in the next rounds? So we have tested our approach in 124 real-world feature models that were used in related works. So this benchmarks has at least 500 variables in the CNF constraints. They have thousands of clauses there, and the number of configurations starts from 10 to the power of 14. And in our experiment, we were interested to compare the results from uniform sampling and from our approach. Therefore, we generated 1,000 samples on all benchmarks with uniform sampling and with our tool with optimization 1 and with optimization 2. The generation with our tool was done in 10 rounds, so we selected first 100 configurations, then we updated weights, selected the second 100 configurations, updated weights, and so on until we selected 1,000 samples. And in comparison, we considered pairwise coverage. The example of results is shown on this table, so we can see that in some of the benchmarks where the uniform, for example, in build root, the first line, the uniform sampling has quite a good coverage already. It has more than 98%. And our approach actually reached the same level of coverage. There was actually exactly the same number of feature combinations covered in uniform and in our approach. There were several other benchmarks on which uniform sampling still has quite high coverage, though our approach were able to slightly improve it. And there were a lot of benchmarks on which uniform sampling showed 75–79% of coverage, while our approach were able to raise it to up to 95–97%. So the histogram on all benchmarks is shown here. So here we compare the coverage of uniform sampling and of the optimization 2. And on two benchmarks, we reached identical coverage. For benchmarks show small increase in less than 5%, though some of them were already quite good with uniform sampling. For example, if uniform sampling can cover 98%, we cannot really expect a high increase with our approach. While on 117 benchmarks out of 124, we have an increase of coverage by at least 15%. We were also interested to check how our heuristics work, so we wanted to explore their effect on the device coverage. Therefore, we compare the results on 3 benchmarks for the base version, where we don't do any optimizations, and of both optimized versions. And in this experiment, we generated 3,000 samples with all versions, and we were making a plot, a cumulative plot for all of the benchmarks. So here is the result on one of the benchmarks. Here we can see that the bottom line corresponding to the uniform sampling actually have the worst results, and actually even with 3,000 samples generated with uniform sampling has worse coverage than 200 samples generated with any version of our tool. The next blue and orange lines show the base version and the optimization one. So we can see that optimization one has slightly worse results than the base version. On the other hand, the optimization 2 managed to outperform our base version. So this heuristics works great on this benchmark. On another benchmark, where we can have quite complex constraints, we see a different picture. So we still see that the uniform sampling is the worst, while the base version clearly outperforms both optimizations, and the difference is quite significant. On the third benchmark, the constraints were quite simple, and we can see that uniform sampling managed to achieve quite a good result of almost 93%. Our approach was still better, but we see that all 3 versions of weight generation reached quite close results in the end. So we can summarize that the base version usually works the best, though it's the slowest one. Optimization 1 usually provides the worst results, while optimization 2 is quite good, it's fast, and on the other hand, on some benchmarks it can even outperform the base version. To summarize, we proposed a novel approach which we call adaptive weighted sampling, where we dynamically modify the probabilities of configurations to be selected for the testing of configurable systems. We have implemented our system and show that it can generate test sets for large configurable systems, and on the benchmarks we show that it can achieve higher device coverage than uniform sampling. As a future work, we would be interested to make evaluation for larger Ts, so for larger sizes of feature combinations. The problem is that our tool can generate test sets for them, and uniform sampling can do that as well. However, it's hard to compute the coverage of test sets, so it's hard actually to compare the results. And another thing we would like to evaluate is the impact on fault detection, so to compare how many faults can the test sets generated with our approach can find in comparison with the uniform sampling. Thank you for your attention.